So we are considering phase equilibrium in a unary system. Unary means it's a single component system. It's a single component system. It has only one component. Now if it has only one component, then something interesting can be done, because we know chemical potential. So mu is the chemical potential, right? So mu is the chemical potential, which can be defined in terms of, we have defined chemical potential various times. So we have defined with respect to, say for example, this is the change in energy with respect to change in mole number of species I, keeping Nj, that is not equal to species I, that is all other species concentrations or mole numbers constant, entropy constant, volume constant. After we defined the Gibbs free energy, we told mu is nothing but change in Gibbs free energy as a change in mole number of, again, mu I. So if I tell mu I is the change in mu I is the chemical potential. So it is the chemical potential, mu I is the chemical potential of species I. Now chemical potential of species I is nothing but partial derivative of Gibbs free energy with respect to mole number of species I. That means how the Gibbs free energy will change as a function of mole number of species I, means if there is a small change in the mole number of species I, keeping Nj, that is all other species mole numbers constant, temperature constant, right? Temperature constant, pressure constant, and all other species mole numbers constant, right? So this is how we define the chemical potential of species I. However, or component I, you can call it species I or component I. But when we have a single species or a single component, we have a single component or a single species or a single compound. So it's like a pure species, right? It's like a pure silicon or pure iron or pure water, right? So it's like a so there is nothing else in the mixture, right? It's only n moles of one component, right? N moles of one component and one component only. So this is basically like we are looking at phase change or phase transition in a single component system, which is a pure system. So in that way it's a pure system. So pure means it can be like pure iron, there is no mixture with carbon or anything else, right? So it's pure iron, or you can think of pure silicon, or you can think of pure alumina, right, or water. So whatever you are talking about here, we are thinking of whether it's a compound or an element, we are looking at pure system, there is no mixture. So note that. Now if that is so, then the molar free energy, so molar free energy is G by N, right? The N moles of one component, right? Only one component. So in a unary system, G by N is free energy per mole, which can also be written as Gm or G bar. Now Gm or G bar is now basically, I can write this as G by N, right? It's an intensive property. So I can write it as delta G by delta N. I can write it also as a derivative of G with respect to N at constant temperature and pressure, right? Del G del N, which gives me mu. So G by N, which is an intensive quantity, it's a molar free energy, that is free energy per mole, is identical with the chemical potential of the component that is present in the system. Since there is one component, then therefore we are not using any subscript here. So we are not using any subscript here, right? Because there is only one component, mu. So mu or Gm now have become one or identical. So chemical potential in a unary system is the same as molar free energy of the system. Okay. Now, as we know that dg is equal to vdp minus sdt plus mu dn, right? dg, right, it's a total differential and it's an exact differential equal to vdp minus sdt plus mu dn, right? In week 4 lectures, if you look at the Legendre transform, how we derive the thermodynamic potentials, and then how we express those exact differentials, right? Where we have mechanical reservoir and thermal reservoir, then it becomes vdp minus sdt plus mu dn. Right, now if since I have a single component, I can write dg by n, okay, which is nothing but dgm, right? So it's nothing but dgm equal to dg by n, which is, again, now if I do dg by n, so everything, volume becomes divided by n, right? Volume by n, so if it is v by n, it is equal to vm. Similarly, s by n, right? All of these are intensive properties because these are ratios of total entropy by total mole number. So this becomes Sm. So you have Vm dp minus Sm dt, but now you have mu, which is already an intensive property, but now you have dn, and you are doing but it's a single component system, so n by n becomes 1, so it is d of 1, so this term goes to, so this term does not exist, right? And dgm is nothing but d mu, right? This is equal to d mu. So, and because this guy goes to 0. Now you have, for a single component system or a unary system, you have d mu, basically you have d mu, which is equal to Vm dp minus Sm dt, right? This is not differential form, right? Change in mu in a differential form can be expressed, so it's again an exact differential, and d mu equals to Vm dp minus Sm dt. And again, it's a chemically homogeneous, right? Because it's a unary single component system, it's a chemically homogeneous system, right? Everywhere chemically it is identical, right? If it is iron, it is always iron, right? Wherever. So iron in BCC form, but the composition is iron, right? The atoms of iron only we are considering in a BCC form, right? In the BCC crystal structure. If it is FCC iron, BCC iron is called ferrite, or FCC iron is called, say, austenite. So austenite or ferrite, all of these are for the pure element iron, right? There is no other component in the mix, right? So that's why I'm again and again repeating, so that you understand the nuances here. This is why we can use chemical potential or molar free energy in an interchangeable way. So basically there is no distinction here between chemical potential and molar free energy, right? So now, as you have already seen before, if I look at from this equation, so if this is the equation that we are talking about, so this is called, say, unary. Say, let us call this equation unary. Now from this unary equation, you can write the partial derivative, right? This is a total derivative, it's an exact differential, it's a total derivative, d mu equals to Vm dp minus Sm dt. Now if I fix pressure, right, then dp goes to 0, and you have del mu del t equals to minus of Sm. Now Sm is molar entropy, which is always positive, right? So change in chemical potential or molar free energy with temperature at fixed pressure is given by minus Sm. As you can see, if mu is plotted as a function of t, so let's look at this curve. If mu is plotted as a function of t, then del mu del t at constant pressure is minus Sm, which is basically the slope of this curve. So if I have this curve, I go to any point and I go to any point and draw, so I basically get the slope. And the slope, as you can see, since Sm is always greater than 0, so minus Sm means it's always negative, right? The slope is negative. As you can see here, the slope is negative. right? The slope has to be negative here, as you can see here, right? So, because this is minus Sm and Sm is greater than 0. Similarly, again, from Maxwell relations or from the different the partial derivative properties, we know that del Sm del T is nothing but Cp by T, where Cp is the molar. Cp here stands for molar heat capacity, right? It is molar heat capacity. Means heat capacity per mole of the substance under consideration or phase under consideration. So, del Sm del T is Cp by T, right? Del Sm del T is Cp by T, and you have del mu del T, which is minus Sm, and as you can, again, I just want to tell you that this is a negative slope, and this is negative because this is minus. There is minus and Sm is always greater than 0. Don't forget this part, right? The molar entropy for this phase will always be greater than 0, right? So if molar entropy is greater than 0, minus Sm is basically going to be negative, right? The slope is negative. So you can check that. But now you have this condition also, right? Del Sm del Tp, again constant pressure, you have Cp by T. Now you can combine these two equations, right? Combine these two. So if I combine these two, what do I get? I get, instead of Sm, I am putting, so I know Sm, so I just do del mu del T. Again I do del T of del mu del T at a constant pressure. So this becomes equal to minus del Sm del T, right? So basically I have del mu by del T, which is equal to minus Sm. So what I am now doing, it's constant pressure, that I am doing del T of del mu del T. Again at constant pressure, this becomes del 2 mu del T square, which is nothing but minus del Sm del T, right? It is del 2 mu del T square, right? Del T of del mu del T is nothing but del 2 mu del T square. I'll just erase this so that there is no space constraint. So basically, again to tell you, del 2 mu del T square with pressure constant is nothing but del T of del mu del T, pressure constant, which is nothing but minus del Sm right, del T P, which is nothing but Cp by T, the minus sign. So del 2 mu del T square is minus Cp by T, right? This is a minus Cp by T. So del 2 mu del T square basically gives what? It gives me the curvature. So this gives me the curvature of mu T curve, right? Gives me the curvature, and this gives me the slope of mu T, which is always negative because Sm is greater than 0. Now, and this gives me the curvature, right? Curvature means basically we are looking at how the curvature, how the shape will look like, right? So because we have a, is it a positive curve? It's a negative curvature, right? In general, Cp is positive, temperature is positive, so minus Cp by T means it has a negative curvature. See, it has a negative curvature. Now let us go to constant temperature. So if I fix temperature, so I'll just remove this part because it will clutter the stuff. I have to share the slides later. So if you see now, del mu del Pt is equal to Vm, right? Because if you look at this equation, unary, right, labeled as unary, you see del mu del P at constant temperature. So if you look at that, this dt is 0 and del mu by del P is nothing but Vm. Now if I plot mu as a function of P, then you get, say, some curve like this. Again, for solid, liquid and gas, it will be different, right? The molar volume change in the solid or in the liquid will be much, much smaller compared to gas, right? So, del mu by del P will give you, it is a schematic curve, it gives you a curve like this. Now, if that is so, again, what is del 2 mu del P square, which is nothing but del Vm del P, right? Because del mu del P is already Vm, so del 2 mu del P square is nothing but del Vm del P, which is minus Vm into beta T, where beta T is the isothermal compressibility. It's the isothermal compressibility. Remember, beta T has a negative sign here, beta T has a negative sign here, and there is also another negative sign here. So, you please tell me whether the slope will be increasing or decreasing. If you look at this curve, this is the slope, right? Is the slope increasing or decreasing? So, this is something to think about, right? You think about it. Now, for an ideal gas, this Vm can be written as RT by P, right? Because PVm equals to RT, right? PVm equals to RT. R is universal gas constant, which is 8.314 joules per mole Kelvin, right? And Vm is RT by P. And now, if you have that, you have this equation. Where is the equation? Here. D mu equals to Vm dP minus Sm dt. Now, if you have this equation, so you are integrating from initial state to final state. Again, I want to tell you, initial state to final state depends only on the states. It does not depend what path has been followed, whether it's an irreversible path or a reversible path, does not matter. So, in the case of ideal gas or perfect gas, sometimes in books it is called or perfect gas. Now, you have d mu, which is RT dP by P, again integrating from initial to final state, which is RT ln Pf by Pi, right? So, basically, if I know the final pressure, if I know the initial pressure, so basically I know the change in mu, right, from the initial state to the final state, or change in molar free energy from the initial state for and the change in molar free energy when between the final state and the initial state, right? Change in molar free energy between the final state and the initial state. Now, I will look at the driving force for phase transition. For example, this phase transition, which is alpha transforming to beta or beta transforming to alpha, again depends on the temperature. Now, if I tell that the temperature of transition is Tc or Tr, then at Tr, alpha and beta are in equilibrium. At Tr, alpha and beta are in equilibrium. Now, think of this, that a solid is converting to liquid. Solid instantly does not, 100 solid does not convert to 100 liquid. There will be, during the process of solidification, you will see that there is a zone between alpha and beta, which is basically having a combination of alpha and beta. So, basically, it is not like, so alpha and beta coexist, right? So, at the transition temperature, at the transition pressure, again, I have to define a transition pressure. Now, at the transition temperature or at the transition pressure, what will happen? The total amount of substance cannot be destroyed. The total amount of substance remains as it is. However, at the transition temperature and pressure, you will have a combination of alpha and beta, right? It's a mixture of two phases, right? However, both phases are unary. That means both phases contain only one component, but both phases are possible, right? At the transition temperature and pressure. Now, if I tell the total number of substance in the system is n, or n moles of total substance is what we are considering. So, I can tell we have out of these n moles, n alpha moles of alpha and n beta moles of beta. So, and we also know that mu alpha Tp and mu beta Tp are basically the molar free energies of alpha and beta as a function of temperature and pressure, right? Mu alpha Tp is the molar free energy of alpha as a function of temperature and pressure, and this is mu beta, which is thing, right? So, n alpha is the mole fraction of alpha phase. Remember, this is not n alpha is the amount of alpha phase. So, basically, if I tell, I know the total amount, which is n. So, n alpha by n This quantity signifies what? So n alpha by n basically tells you a fractional quantity, that is a quantity which is basically the amount of alpha in terms of mole fraction. Again, if I know the density or molar volume, I can also convert it to volume fraction, right? So basically n alpha by n quantifies the amount of alpha phase in the system, or the fraction of alpha phase in the system, or phase fraction, right? N alpha by n. So this is fraction of alpha phase. Is a fraction of alpha phase. Similarly, n beta by n is a fraction of beta phase, right? Now, if I know mu alpha is the molar free energy of alpha phase. Now, if I multiply with the amount of moles of alpha phase, that is n alpha, so I get G alpha, which is n alpha mu alpha at a given temperature and pressure. Similarly, I can write G beta equals to n beta mu beta. Now, total G is G alpha plus G beta, which is n alpha mu alpha plus n beta mu beta. Now, if I have this, I can basically write a differential. So, this is dg alpha plus dg beta. So, now I can first collectively, I can first calculate dg alpha. What if this is g alpha and this is g beta? So, basically what we want to see is dg alpha is minus s alpha. Again, this is Sm, right? Molar entropy. So, molar entropy of the alpha phase times the amount of alpha phase times dt. Again, Vm alpha n alpha dp and mu alpha dn alpha, right? Mu alpha dn alpha, right? This n alpha, please note that this n alpha does not denote a component but the amount of phase alpha present in the system. Similarly, I can write for dg beta, which is minus s beta n beta dt plus Vm beta n beta dp plus mu beta dn beta. Now, the degree or extent of transition, right? The extent of transition again is given by the internal process variable, or this extent of transition now I can define as zeta, which is an order parameter, which is n beta by n, right? So, this is the extent of transition from alpha to beta. We are writing zeta, which is n beta by n. Now, if you and 1 minus zeta is n alpha by, right? Now, see, zeta is an order parameter which basically tells you the amount of beta phase and the amount of alpha phase in fraction, right? Phase fraction of alpha phase fraction of beta phase in terms of moles, right? If we give the molar volume information, then we can also give it in terms of volume fraction of the phase, right? In terms of volume fraction of the phase. Now, at constant temperature and pressure, as you know, dg is mu alpha dn alpha plus mu beta dn beta, right? All this sdt and vdp, that dp dt all go to 0, right? So, dg just becomes mu alpha dn alpha plus mu beta dn beta. Now, zeta is mole fraction or volume fraction of beta, right? That's what we are telling, right? So, zeta is the extent of transition, but zeta can also be defined as the mole fraction or volume fraction of beta. Now, if I express G of the mixture in terms of N, P, T and zeta, then I can write this is N alpha. So, you have G, right? So, it is G is N alpha mu alpha, right? So, basically I am writing N 1 minus N into 1 minus zeta, right? 1 minus zeta is basically the mole fraction, right, which is n beta by n, right? So, 1 minus zeta is n alpha by n, right? So, into mu alpha, right, into mu alpha, right? And this is the G, and this will be n zeta mu beta as a function of temperature and pressure. Now, if I write this, basically I can write this like alpha is my parent phase, so I can take alpha phase out. So, this becomes n mu alpha Tp, right, n mu alpha Tp plus n times zeta, where zeta is a internal process variable which represents the volume fraction of beta, n zeta times mu beta minus mu alpha, right. So, if I take n zeta common, so n zeta common, then I have mu beta minus mu alpha, right, mu beta minus mu. Now, if I do this, then I can write mu as a function of Tp and zeta. Zeta is the order parameter, which is equal to G by n, Tp and zeta, which is basically mu Tp basically gives you mu alpha Tp and zeta times delta mu Tp, right? Delta mu is nothing but a chemical potential difference, which is basically mu beta minus mu alpha, right? So d mu, we can also write del mu del zeta is basically delta mu, right? So we can write d mu as a function of temperature and pressure is nothing but delta mu times d zeta, right? And the driving force, right? Driving force for this alpha beta transformation is given by minus of del mu del zeta or del g bar del zeta, which is basically nothing but at constant temperature and pressure, which is nothing but delta mu, right? Delta mu is the driving force, minus of delta mu, right? Minus of delta mu. And this we can clearly understand, right? Minus of delta mu is the driving force, right? So because if there is a chemical potential difference or if there is a potential difference, then something flows, right? And the driving force is the negative of this potential difference, right? So d is equal to minus of del mu del zeta. Now if I think of this, I have this beta phase. If you see this clearly, this is my beta phase and this is my alpha phase. Now you see we have this transition temperature TTR, right? And this is my beta phase. And this is my alpha phase. So this is my alpha phase, this is my beta phase, and beta phase is transformed to alpha phase. So beta phase is transforming to alpha phase, or alpha phase can transform to beta phase. Now think of this, d is minus delta mu, right? And delta mu is mu beta minus mu alpha. Now if just look at this picture, now if you see there is a transition temperature at which this is the alpha beta coexistence. Right, this is the alpha beta coexistence point. Now, if you are below TTR, you are seeing beta is having more energy per mole than alpha. So, beta will transform to alpha, right? Beta will transform to alpha. Now, so here beta will transform to alpha and d is equals to minus delta mu, right? So which is basically minus delta mu, which is mu beta minus mu alpha. Mu beta is greater than mu alpha, so beta will transfer to alpha. Now if I go above TTR, so basically d is minus delta mu, but now you see that the alpha phase has higher energy than beta phase. Alpha phase has higher energy or higher mu than beta phase. So this is mu beta minus mu alpha. So as you can see, this is minus of delta mu, where delta mu is mu beta minus mu alpha, which is nothing but mu alpha minus mu beta, and mu alpha minus mu beta is positive. So as a result, alpha will try to transform to beta along this line, right? Alpha will try to, means along some line, along some path, alpha will try to transform to beta. So as you can see, below Tm, it is beta which is having higher chemical potential, or beta which is having higher molar free energy. On the other hand, when you are above, well above transition temperature, you see that the alpha phase, right? This is the alpha phase, this is the alpha point, and this is the beta point. So basically, definitely the beta phase has lower free energy than alpha, and the driving force is such that alpha phase spontaneously transforms to beta, right? Here alpha phase spontaneously transforms to beta, here beta phase spontaneously transforms to alpha here. So beta transforms to alpha here, and alpha transforming to beta is here, right? Now, if T is greater than transition temperature, as you can see, this is what I have written here, mu beta is less than mu alpha, delta mu, which is mu beta minus mu alpha, is less than 0. So, D is minus delta U, which is greater than 0, right? Which is basically greater than 0. So, alpha phase, that means what? So, basically what I am telling is, if T is greater than TR, then alpha phase is basically D is positive, right? D is positive. That means alpha phase is thermodynamically unstable. as you can see here, thermodynamically unstable and transforms to beta phase. So if T is greater than Tm, mu beta is less than mu alpha, right? It has the lower free energy or lower free energy per mole. Now delta mu is the driving force, which is mu beta minus mu alpha, which is like basically less than 0. So minus of delta mu will be greater than 0. Minus of delta mu is the driving force, and that is greater than 0. So as a result, what happens if the driving force is greater than 0? Alpha phase is thermodynamically unstable and spontaneously transforms to beta phase. Now think of if T less than Tr, then mu beta is greater than mu alpha. So delta mu, which is again mu beta minus mu alpha, is now greater than 0. So D, which is minus of delta mu, is less than 0. Now if that means what we are telling is if T is less than Tr. So see, this is where T is greater than Tr. This is the case. T is greater than Tr. Now I am going to T is less than Tr. So this is the case. Now think of alpha changing to beta, which is thermodynamically not possible because alpha is a more stable phase, beta is the unstable phase, right? So alpha is the thermodynamically stable phase. So alpha does not transition to beta. If alpha transitions to beta, it will require if alpha is transformed to beta, then it will require some sort of a push from outside so that alpha can transform to beta, right? It has to be, it cannot be a spontaneous process. Alpha to beta transformation when T is less than TCR, alpha to beta transformation when T is less than TCR is definitely not a spontaneous process. Why? Because D is negative and alpha itself is a thermodynamically stable phase. So if I want to convert a thermodynamically stable phase to a thermodynamically unstable phase, then basically I require to supply some enormous amount, means I don't know, means we haven't quantified yet, that we will quantify, but D is less than 0. So it is impossible for alpha to spontaneously transform to beta. However, it is possible to do some work on the system, so such, right, do some chemical work or some such work or mechanical work on the system so that the alpha phase, which is a thermodynamically stable phase, transforms to a beta phase, right? In general, without any external force, without any external stress, this type of transition will never occur spontaneously, right? Without external stress, as transition does not occur, that means it is not a spontaneous or a natural transition. Our natural transition is the one which does not require any external push, right? It does not require any external push. Remember the sign. If D is positive, then alpha phase or the right, if D is positive, which is basically mu beta minus, which is negative of mu beta minus mu alpha, you can immediately understand that alpha phase is a thermodynamically unstable, right? So basically if I telling mu beta minus mu alpha and T is greater than Tr, if T is greater than Tr, alpha is a thermodynamically unstable phase, right? Alpha is a thermodynamically unstable phase and it transforms to beta phase, correct? But here alpha to beta transformation, alpha itself is a thermodynamically stable phase and it has to transform to beta, which is not possible spontaneously. However, in a non-spontaneous way, if it is possible, then you have to make some work done. You have to make some work and provide some work from or external force from outside for this reaction to happen, and that force can be very large, and because alpha is the ground is the minimum energy state here, right? So alpha is the more stable phase than beta phase. So alpha does not transform to beta spontaneously. So we will just add this term spontaneous. Okay, so if T equals to transition temperature, as you know that mu beta, that is the molar free energy of or chemical potential of beta or molar free energy of beta, because it's a unary system, equal to molar free energy of alpha. And therefore delta mu is basically 0. If delta mu is 0, driving force is 0. If driving force is 0, alpha and beta are in equilibrium and the transformation from alpha to beta or beta to alpha are equally likely. On the other hand, if T is greater than TTR, then mu beta is less than mu alpha, right? If mu beta is less than mu alpha and delta mu is less than 0 and D is positive, and as a result alpha phase, which is thermodynamically unstable at this temperature, right? T is greater, alpha phase, which is thermodynamically unstable at this temperature, will transform to beta phase. So in this case, so we can write what is delta SIR, which is basically nothing but d by t, which is basically mu alpha minus mu beta by t, which is minus delta mu by t. Now delta SIR will be equal to 0 at t equal to T. Right? Now note that how will this transformation, at what rate will this transformation take place? We can now use a kinetic theory and tell del zeta del t is proportional to d by rt, right, where d is the driving force, right, d is the driving force. Del zeta by del t we can write is proportional to, not r is not required, d by t, d by t. So and d is the driving force, remember. So it is basically now telling the rate at which this transformation will take place, or rate at which the liquid will starting liquid will completely convert to a starting solid. Say for example, or a starting alpha will completely, when alpha is thermodynamically unstable. So alpha is thermodynamically unstable where? When the alpha is thermodynamically unstable when T is greater than Tr. Right? So it will spontaneously transform to beta, but at what rate it will transform is basically, you can, if you want that, then you can insert this time, right, on this internal process variable or order parameter. So this is basically evolution of order parameter. This is evolution of order parameter as a function of time, which is proportional to d by t. Again, you don't have to care about the kinetic theory at all, but what I am telling is that the how zeta will transform is a part of kinetic theory. It is not a part of thermodynamics, but in thermodynamics means or equilibrium thermodynamics, but in equilibrium thermodynamics, one thing you have to always appreciate, that when we are talking about thermodynamics, we are talking about driving forces. We are defining driving forces, right? And this driving force, basically, if it is positive, then you do have, so if the driving force is positive, then basically there will be a spontaneous transformation from one phase to the other, right? Because the first phase, the initial, so when d is greater than 0, we can immediately see, means we can immediately understand that the phase that has high energy is the unstable phase, and we are looking at that unstable phase as starting point, and we are trying to transform it to beta phase. However, this will proceed as a function of time. How fast or how slow is not in the ambit of thermodynamics, right? So you have to use the kinetic theory, and so as a result, we can write this type of equations, right? So this is now if I write this equation, del zeta del t, where delta SIR is already defined as minus delta mu by t. Now if you can see, dSIR by Vm, right? What is d? Delta S is d by t, right? Delta S is d by t, right? So what I am trying to say, and zeta, d zeta is what we write, right? So basically what I am trying to say is that this I can replace with dSIR. So dSIR by Vm dt equal to d by t del zeta. So d by t del zeta or d zeta Vm dt, right? So this is basically rate of, so this equation is called rate of molar entropy production, which I will describe later, right? Rate of molar entropy production. Now, if we think of driving force as a function of temperature and pressure, then you can see the driving force, if you look at d mu alpha, so you have again, you are looking at the transformation from alpha to beta or beta to alpha. Or beta to alpha. Now, if you look at d mu alpha, which is minus s alpha dt plus Vm alpha dp, and d mu beta, which is minus s beta dt plus Vm beta dp, then you can write d of mu beta minus mu alpha. So basically this is your equation, say 2 and this is 1. This equation number is 1. And then what you are doing is 2 minus 1. So you get d mu beta minus mu alpha equals to minus s beta minus s alpha dt plus Vm beta minus Vm alpha dp. Now, which is basically d mu beta minus mu alpha is nothing but d of the delta mu, right? So d of mu beta minus mu beta minus mu alpha is nothing but delta mu, right? It is nothing but delta, which is basically s beta minus s alpha, which is minus delta s dt, and delta Vm dp, right? Which is Vm beta minus Vm. That's it. Right, now you can integrate, so you know the del d of delta mu, so you can integrate delta mu as a function of, say, for example, the time. So you can take limits as, say, you can think of P naught as the pressure, right? It's like P naught can be 1 bar, right? P naught is the reference pressure and TR is the transition temperature, and you are integrating up to some temperature T. Now if you have that, it becomes minus delta STP dt plus Vm. Right, again here P0 is the standard pressure, and now you are going to P bar, and here T is constant, as you can see. So P0 to P. So here we are looking at delta Vm dp, and here it is delta S dt. Now at equilibrium, delta mu has to be equal to 0. Now assume that for a phase transition, delta Cp is constant, right? There is no difference in delta Cp. So basically what I am trying to say that, and beta T and alpha are also 0. So I am simplifying the problem as much as possible. So I have taken the isothermal compressibility to be 0, alpha to be 0 or insignificant. And we are telling that for a phase transition, delta Cp, there is a change in heat capacity for or the difference in heat capacity between the alpha phase and the beta phase are basically, we are assuming it to be constant, right? Now in that case, I can write so from here I can write delta STP equals delta S0 at T transition, right, at the transition temperature, and at P0 plus we can write delta Cp times ln T by T, right? So that is your delta STP. Now you can also, so right, you require the delta STP information, right? You require the delta STP. Now this is how I am defining it, right? Because delta STP is nothing but the delta S0, which is basically the change in entropy at standard state, that is, which is a function of transition temperature and P0, right? And then there is this delta Cp term with ln T by T0, right? Why this ln T by T0? Why? Because we are looking at integration here, and we are telling that there is a so where from Cp dt is coming, this term is coming is from del S del T, which is basically Cp by T, right? Del S del T equal to Cp by T. So you are using this and you are using this, and then if you integrate, and now you have the molar volume, again the molar volume change at T and P, we are telling that it is the same as that at P0, and that is basically the same as delta Vm0. Now delta S0 is a change in molar entropy at the transition temperature, and P0 means P0 is the standard pressure, and delta Vm0 is a change in molar volume at transition temperature, and again the P0 bar, which is the reference pressure, right? Reference pressure is P0. P0 can be 1 bar. Then delta mu I can integrate, and again if you remember that this is very simple because we have taken alpha and beta T to be 0. Okay, as for simplicity. Now you can integrate this, and basically you get delta S0 here, delta Cp here, and delta Vm0 here, right? And there is a, because Vm dp, right? Vm dp. So delta Vm dp. So dp is basically P minus P naught. P naught is your reference pressure. P naught is your reference pressure in bar, or it can be in atmosphere. But remember, P naught can be 1 bar, it can be 1 atmosphere, it can be anything. And TTR is your transition temperature, where both phases are in equilibrium. right? And now you are looking at delta mu. Now delta mu basically gives you the driving force, right, which is mu beta minus mu alpha, right? So it is giving you the driving force because D is minus, what is D? We have defined it. D is minus of delta mu, right? D is minus of, so you have D minus of delta mu, and mu is nothing but here, although we are talking about this delta mu is nothing but delta G bar. We can call it also delta G bar or delta Gm, which is Gm beta minus Gm alpha, right? So this is delta mu is basically the difference in chemical potential between beta phase and alpha phase, or difference in molar free energy between beta phase and alpha phase, which is related to difference in entropy at the temperature of interest and pressure of interest. And only thing, when we do the integration, please note that you have to take not only the transition temperature, this is something sometimes you miss, that you have to take the transition temperature as well as the pressure, right? You also have to take the so in the case of dt, your pressure is fixed at P0. In the case of dP, your pressure change is also accounted for. P0 to it goes to P, right? And then you do this integration and you take into account this equation. So this is the equation, so that it comes to delta Cp ln T by Tr. Now once you have done all of these and you have defined or you know these quantities, then you can basically calculate delta, right? Delta mu. Only thing, remember, in this formula you can make it more complex. You can take Cp as a function of temperature, you can take alpha, you can take beta T, that is the isothermal incompressibility, and then you will get basically, so then you will get a slightly more complicated equation for delta mu, right? Slightly more complex equation for delta mu. Now, if I look at this, you do a little bit of algebraic manipulation, which I have done here. Say, for example, I have taken T by Tr to be Z. So, Z is, so dZ is 1 by Tr dt and all this stuff. Then basically what you get is delta. So, delta mu, that is the change in chemical potential between alpha phase and beta phase, is basically related to the difference in the heat capacities of the two phases. Delta is 0. So, delta is 0 is the difference in entropies of the two phases at the reference temperature and reference pressure, and then there is a T minus Tr, right? Tr is the TTR is the transformation temperature. Plus minus you have this term, okay? So, it is like delta Cp T ln T by Tr. If you go through this, derivations, you will easily understand this part, and then this is nothing but delta Vm0 P minus P naught, right? So, now remember delta is 0, and we have seen that just for the ice water problem and also other problems we have seen that. So, delta is, so at constant pressure delta is 0 is nothing but delta is 0 by TTR, right? So, basically if that is so, because delta Hm, as you can see here, is equal to TTR delta Sm. So, delta Sm is delta Hm by TTR. So, basically now you can write this equation, delta Cp delta T minus delta Cp times T delta T by Tr, which is delta, so take the delta Cp common, delta T common, so this becomes 1 minus T by Tr, which if I integrate, which I get minus delta Cp delta T square by Tr, right? Because I get minus delta, so you have delta Cp, where is that? So when I am integrating, so remember what I am trying to do here is this. I am telling, so here you have delta Cp delta T minus delta Cp T delta T by Tr. So when it becomes delta T by Tr, it has, one second. So I have taken a small difference. So basically you have this T ln T by Tr. Ln T by Tr is gone. So you have this. So you just require to take delta Cp delta T is common. So this becomes 1 minus T by Tr, which is basically going to be delta T by Tr. So if I integrate, I get, So delta mu equals to minus of delta H0 plus delta Cp delta T by Tr into delta T, right? And delta Vm0 delta P. Now remember, this is one thing where there is an ln and you have done this. So how did you do this? You have ln here, delta Cp is here, T minus Tr, and then there is a delta Cp T ln T by Tr. So now we have taken this term. Yeah, so if you integrate, you get this term. So delta mu basically has a delta H0 term. There is a change in enthalpy at the transition temperature, and then it has this delta Cp delta T term. And so basically this is nothing but a little bit of algebraic manipulation where we are talking about Cp and the difference in specific the heat capacities, but we are not considering this part. As you can see, it is simply delta Vm0 into delta P. We are not considering any effect due to thermal expansion or isothermal compressibility, right? So that's next, in the next lecture I will talk about order of phase transition, and also I will introduce this phase diagram and the Clausius-Clapeyron equation.